welcome back to Physical Geology, and today I want to go over the Plate Tectonics lab that I posted on Canvas for you. What I want you to follow, we'll just kind of go through some of this and I'll give you some guidelines as to how to complete this lab. Remember, I always ask this question here as essay question. The three basic concepts, know those. I don't want the three plate tectonic boundaries, I want the three basic concepts, and they're right here. Looking at this figure here, what I want you to focus on are a couple of things. Are red and green dots, and even the blue dots, which really don't show up here, but they show up down here. And these are earthquakes. These are the focal depths to earthquakes. And note that at subduction zones, at ocean trenches, they start off shallow and they get deeper as you go into the subduction zone. And so there'll be shallow focus, intermediate focus, and then the deep focus earthquakes down here from 300 to 700 kilometers. And so this is what we call the Benioff zone, the Watati-Benioff zone. And we'll be doing an exercise on that. The key thing, it documents, this type of fault is a reverse fault, right? A reverse fault where the overriding or hanging wall is moving up over the footwall or the descending ocean lithosphere here. Also note that at divergent margins and transfer margins, we only see shallow focused earthquakes. And then you can see some of these numbers, the ocean lithosphere is anywhere from 70 to 100 kilometers thick. You can't really see it here, but continental lithosphere is a little bit deeper. It goes then up to about maybe 130 to 150 kilometers thick. The other thing to note is in this lab, we'll be talking about the origin of magma. And note there is this hydrous flux partial melting here, which occurs in subduction zones only because the ocean lithosphere is hydrated by hydrothermal circulation at the mid-oceanic ridge. And this hydrated lithosphere, mostly in the serpentine minerals and some amphiboles that are hydrated, once you get into the subduction zone, that water leaks out right around 100 kilometers, causes the melting point of the mantle wedge, peridotite above it, to lower, so that temperature of melting lowers, and you get partial melting, anywhere from 2 to maybe 10% part of it, and that produces magmas at subduction zones. The other type of melting is we see the decompression melting, partial melting at divergent margins. And here we're just taking hot rock, which is solid in the mantle, but when we move it to shallower levels at these divergent margins, it's going to partially melt, and you'll see how that works here in this lab here. Now, the other thing to note, I do have a question on the study guide about the rates of tectonic plates, especially the mid-oceanic ridges. So if we look at the mid-Atlantic ridge, its spreading rate is anywhere from 3 to 2.5, maybe 3.5 centimeters per year, right? So about the rate that your fingernails are growing. But note that the East Pacific Rise over here, it's anywhere from about 6 to 13.5 here. So it's much faster spreading rate. Also note on this diagram that these lines with the teeth on it, the barbs, those indicate reverse faults or subduction zones, convergent boundaries here. So over this part here, I talk about partial melting and kinetic theory. Make sure you read about this. And then I talk about decompression melting and this confining pressure. And we'll kind of go through that. And I talk about hydrous flux melting. Again, I do all this in my video lectures as well. So let's look at this first problem here. This one's going to ask us to figure out the rate of seafloor spreading for the mid-Atlantic ridge here. And so I have the document camera going here. The first question is, we want to measure the distances between points B and C in kilometers today. And note there's a scale over here. So one important thing to do first is figure out our scale. So here, when I put this ruler up here in centimeters, I see, so it looks like 3.7 centimeters is 2,000 kilometers. So that's our scale. So 3.7 centimeters is 2,000. And so what I want you to do is, I want to know what 1 centimeter is. So I want to divide both sides by 3.7. And when I do that, I'm going to get 1, so this becomes 1 centimeter will equal some distance. So to do that, we'll get our calculator going. The 2,000 divided by 3.7. So 541. So each centimeter is about 541 kilometers. All right, so that's going to be our scale we'll use for measure. So now they want to just measure between B and C here. And so we do that with our ruler. We'll measure the distance between B and C. And so that distance is 7.5 centimeters. 7.5 centimeters. And we know that each centimeter is 541 kilometers per centimeter. So we're going to multiply these two numbers. So it's about 4,058 kilometers. So that's our distance. So we'll put that number here. 4058 kilometers. So note that the isochronous at C, this line right here, and the isochron at B, this line over here, they both sit on the boundary between the Jurassic and Lower Cretaceous ages for the seafloor, and those isochrons are 145 million years old. So that's the time we have there. So we know the distance, which is 458 kilometers, and we're going to divide that by the time, which is 145 million years. And that's going to give us our distance, in this case, in kilometers per million years. So let's do that there. So we got the 4,058 kilometers divided by the 145 million years. And that's going to equate to about 28 kilometers per million years. So we get 28 kilometers per million years. Right, so we've just solved this first problem. We calculate the rate, and it says 145 right there. Now, this is just going to ask us to convert it into centimeters per year. One of the rules that I have is when you have something like this, when you have a kilometer per million years, that's going to be the same thing as millimeters per year, right? Millimeters per year. When you do all this math, you can do the math, do the conversions, but you'll see that it's going to be millimeters. So essentially, this 28 kilometers per million years will essentially be 28 millimeters per year. But note that we want it in centimeters per year. We know that there are 10 millimeters in 1 centimeter, so the answer we want here is 2.8 centimeters per year. And if you think about that number, that's going to fit very closely for our mid-Atlantic ridge spreading rate, 2.5 to 3.0. So we're right in the middle there, right? So we've calculated a number that's very similar to what we're seeing in the real world here, right? What I'd like you to do next is you're going to do the same thing for points D and E. So for problem 3, you're going to be using this rate. The rate I want you to use, let's use the 28 kilometers per million years. You want to use that rate. So we're going to figure out when Pangea broke up here. So the time is going to be the distance that you measure, in this case from points D and E. So note that D is here in Africa and D is over here in North America. And when we look at those ages, well, we don't know the ages. We're going to calculate that, but we know we can measure their distance. So again, measure that distance between D and E, and that's going to be this distance here in kilometers, right? And then we're going to divide that by the 28 kilometers per million years. And then the kilometers cancel, and your answer will be in will be in time, millions of years. So your job is to figure this one out there. All right, so the next part here deals with this decompression melting and hydrous flux melting, and it really looks at this next figure on the next page here, but we're going to look at figure 3, and we're going to look at this point X, which is represents a mass peridotite buried to 80 kilometers, right? So there's our point X right there, which is about 80 kilometers. The question they're asking us is, according to this continental geothermal gradient, rocks buried to 80 kilometers beneath would be at what temperatures? Beneath a continent, right? So if we go down to 80 kilometers, which is right around here, because that's at point X, on this continental thermal gradient, we see that the temperature would be around maybe 700 degrees centigrade. And then for the geothermal gradient, you see it's a little bit higher heat flow in the oceans. We see we got maybe about 1,000 degrees centigrade. So that's how I'm just reading those graphs there, right? So for ocean, I just go up, it's about 1,000. If your peridotite at point X, is it a mixture of liquid, partial melt, or is it a massive solid? And if we look at it, note that point X sits to the cooler side of this peridotite solidus. So whenever you cross this line, you're going to see partial melting. If you're on the cooler side of that, you're at 100% rock, right? So we have 100% solid rock. And how do you know? It's x to left of, and let's call this the dry solidus. So this line really, we should probably add the word dry here. Dry solidus, because this is for when there's no water being introduced to the mantle. For example, like in decompression melting. Note that I do have the wet solidus over here, and that's going to come in a little bit later. Then as we look at the diagram here is let's say we take our point X and we move it up to 1750. So you'll move it up to 750, and then you'll move it up to 2250. And so you just tell me what happens when you move to different temperatures, right? See what happens there. And then for question B, where they talk about pressure in kilobars, right? So about 30 kilometers of barrel depth is about 10 kilobars of pressure. So at 80 kilometers, so if we look over here, atmospheres are essentially bars, and so 1,000 bars is 1 kilobar. So 10,000 atmospheres is really 10 kbar, 10 kilobars. So they want to know for our peridotite at point X here, at 80 kilometers, what is the kilobars? And so if we bring this over, we see it's right here. So it's around 25 kilobars, right? So around 25, somewhere between 20 and 30 here. So we would say down here, we're at about 25. All right, so now the next thing is we're going to be looking at what depth and pressure will the peridotite begin to melt if it is uplifted closer to the surface. So this is simulating what would happen at a divergent margin. And we're going to keep the same temperature. Again, we're looking at this point X here. So if we take this and we start this point X and we start moving it toward the surface at that same temperature, we see that we're going to hit the dry solidus right there. And that's where we're going to begin to partial melting will begin right there, because we're going to cross that line and we're going to enter this partial melting field. So that's happening at a pressure around 10,000 kilobars, and here in this case maybe at around 30 kilometers depth, right? So that's what it's asking us there. So we're around 30 kilometers and about 10 kbar according to that. And how much partial melting? Well, if we're right in here, so note that for the partial melting, 25% would be something like that, 50% there, 75% here. So we're barely in maybe the 2 to 3, maybe 5%. So we'll say around maybe 2 to 5%, right? So according to this graph here, we're really just barely cross the line. If we move closer to the surface, we can get up to 25% there, right? Okay, so that's kind of how we're going to read that graph here. And so now your job is to tell me what name we apply to this type of partial melting, whether it's hydrous flux or decompression, and then where would you think this is happening? What type of tectonic setting is really what we're looking for here. And then for letter C here, based on your answers above, what two changes can cause the peridotite to melt? And well, we know one, we had more temperature. We can just make it hotter. That can cause partial melting. The other one is we change the pressure, right? So you want to put something down to that effect there.